Hi, this lesson is on a topic called linear least squares regression. It's found in sections 6.4 and 6.5 of the text, and this material follows very closely on the heels of the topic of correlation that we discussed last time. And this will finish chapter 6 for us this lesson. Before I go to the lecture notes for this particular topic, let's look at an Excel spreadsheet that contains the same data that we were looking at last time, in fact a little more. These weights are the weights of cars, and the mileages are their EPA tested gas mileages. The weights and mileages are the same data that we looked at last time. And we discovered that the correlation between weight and gas mileage for these cars is pretty strong negative. R turned out to be about negative 0.87. So the thought comes to mind that perhaps we could use that relationship to our benefit to be able to predict mileages using weight. So for example, along comes a car that weighs 3,600 pounds. Approximately what would its gas mileage be? So let's look at the mathematics that would allow us to do such things. First of all, let's look at a scatter plot here and show how to get what's called the regression equation, the mathematical relationship between weight and mileage. I'm going to insert a scatter plot, and when you do that, Excel takes a guess at which variables you want to graph. Depending on how many variables you have and what the relationships between the columns containing them is, Excel may do a good job or a poor job of guessing which graph you wanted to do. In this case, this is not what I had in mind necessarily. So if this happens to you, here's how to clear Excel's default choice out and make your own. Come to one of the data points, left click on it, and then right click and select data. And now, right now, Excel has graphed mileage and engine size. Actually, mileage is what I want. I don't want engine size at the moment, but I'm going to click remove, click on engine size, click remove, and start over from scratch. I'll click add. The series name then is going to be mileage. That's the variable, output variable being graphed. Click on the box for series X values, and then I'll come up here and click, hold, and drag down through all of the X values that I want to graph. Then come over and click on this box, clear out what's there, come back and click and hold on the Y values, drag down through the mileages. Alright, click OK, and again. And here are the mileages graphed as a function of weight. Weight is on the x-axis, mileage is on the y-axis. Right now, Excel has chosen to make 0, 0 the origin here at the left corner, and then it hasn't used the graph paper very effectively. The data points are lumped here in a small range. So let's see if we can change the scale on the axes in order to better use the paper. If I come down to the scale, and one of the numbers on the scale, and left click, and then right click and click Format Axis, I can come up here, and right now they are automatically, the units are automatically being chosen. I can choose Fixed instead, and if you look at the weights, the smallest weight was a little over 2,000, so I could start the weights at 2,000. And as far as how high to go, a little over 4,000, so 5,000 maybe is maybe not a bad choice. Alright, so that stretched out this axis to go from 2,000 to 4,500 now Excel chose. And if I come over here and click, left click, and then right click and Format Axis, again, I'll choose a new minimum. The smallest engine size is something like 17, so I could start here at 15. And there's a much better scale to use than what Excel initially chose. Now let me come over here on one of the data points, left click again, and now right click and click Add Trend Line. We're going to have Excel put in the best fit line. Actually, Excel could put in a number of different types of curves. A line is the most common choice and the one we are going to deal with. And so Excel proposes linear, and I'll stick with that. Down here I'm also going to have Excel display the equation on the chart and the R² value on the chart. And I'll click Close. Alright, so this line then attempts to go close to as many of the data points as possible. It's the best fit line in some sense. And here is its equation. Let me drag it off to the side here where we can see it better. It reads y equals negative 0.0071x plus 44.238. X values are weights, y values are mileages, and this is the equation of the line that Excel drew. The R from before was about negative 0.81, and so sometimes you use what's called R², which just is to take that number and square it, and you get about 0.76 here. So that's how you can find the regression equation. Let's do the same thing another way. If I come up here to the Data tab and Data Analysis, I've already gone through the procedure to add the Data Analysis add-in to Excel. And let me choose Regression out of this list. So I click OK, and it says, first of all, input the Y range. I think its choices were correct in this case, but let me show you how to do it. So input the Y range. I'll scroll down through the Y values. Input the X range. Click, hold, drag down. And then the boxes here can remain as given. I come down here, I'm going to click Output Range to have Excel put its output here on the sheet where we can see it. And I'll click here and then click somewhere to an empty space on the worksheet. So for example in cell E1, and that tells Excel approximately where to put its output. Then I'll click OK. Move this graph out of the way. And here is a data table of a lot of information. In particular, the coefficients of the regression equation are here again. There was a negative 0.00708, remember, and a 44.237. So the way you read this, the line is of the form y equals a plus b times x. That's slope-intercept form. And a, the y-intercept, is right here, the 44.23. And the m, the slope, is the negative 0.007. There are many other things here in the table as well. In particular, right here is the R² if we wanted that. Okay, so here are a couple of ways to get the regression equation and the R² from Excel. Now let's go to the worksheet for this section. Here's the data again. At the bottom is an illustration of the scatter plot that we got from Excel. And the regression equation and the R². Okay, let's first briefly talk about where that comes from. You don't want to do these computations by hand. Again, if the regression equation is of the form a plus bx, the way to get the slope and the y-intercept, the slope is b in this notation and the y-intercept is a. First of all, you have to come over here and compute the mean of all the x values, the weights in this case, the mean of all the y values, the mileages of this in this case, then the standard deviations of both of those variables, then the Pearson R, which itself was quite a bit of computation, and finally here are a couple of formulas to apply. So I might have you do one homework problem where some of this is already done and you kind of use these formulas to fill in. But for the most part, we're doing all of this by software. What is the predicted highway mileage of cars of the following weights? Here's the question then that I was posing earlier. Suppose I know that a car weighs 3,100 pounds. What kind of gas mileage can I expect out of it? And here's a car that weighs 3,300 pounds, and what kind of mileage would it be able to get? Let's copy down the regression equation. Y equals 44.2 basically minus 0.00708 times x. And this is our x variable, our independent variable. This is our y variable, our dependent variable. So now I take the regression equation, and for x I plug in 3,100 pounds. And this works out to be 22.3 miles per gallon. Okay, is that going to be exactly the mileage this car gets? Probably not, but it's certainly better than no information at all or taking a random guess. If you do the same thing but plug 3,300 in for x, you get 20.8 miles per gallon. So heavier car, smaller gas mileage. Maybe you have had the experience of going camping with somebody who knew the following trick. You wake up in the morning, and while you're showering, your friend, so-called friend, sneaks over and puts like a 5-pound rock in your backpack, and then you hike all day, and when you get to the campsite in the evening, he goes over, walks over to your pack and pulls out the 5-pound rock and says, "Surprise, how'd you like carrying this all day?" So here's a variant on that. You go to a friend's car, you pop open the trunk, and you put a 1-pound weight somewhere hidden in his trunk. You close the lid and you let him drive it for a while. What would happen to your friend's gas mileage? Well, first of all, your friend probably wouldn't even notice because the effect of a 1-pound weight is going to be very small. But something should happen, right? Heavier cars get lower gas mileage, and so this should lower your friend's gas mileage. Why you would want to do that, I don't know, especially if it's your friend. On the graph that we saw before, we had weight and mileage like this, and the slope was negative. The graph sloped downward. And so think about what slope means. Slope means rise over run. And so what we've done is put a 1-pound weight in the trunk. Weight is the x variable. In other words, the run is 1. We added 1 pound. And now I know that the slope is rise over run. That's rise over the number 1. But I know what this number is from Excel. The slope is negative 0.00708. And rise over 1 is just rise. And so the rise is, in this case, a negative number. And it's the answer to the question. Putting a 1-pound weight in the trunk of somebody's car would tend to decrease their gas mileage about 0.00708 miles per gallon. Decrease because it's a negative number. Again, nobody would notice that, but you could use the same technique to talk about what would happen if you put 100 pounds in the trunk of the car, or 500 pounds in the trunk of the car, and then the rise would become a significantly large negative number, and the mileage would definitely noticeably decrease. Remember, garbage in, garbage out. So this is pretty powerful. You can use the computer to get a regression equation and proceed to use it. And if you're doing things right, that's a very valuable thing to be able to do. If you're doing things wrong, that's a very dangerous thing to be able to do. You can get garbage answers and not know it. Here are a couple of situations. On the left was the picture that had r equals negative 0.99, and on the right was the example that had r equals 0. So you can take these data points if you had their actual numerical coordinates, go to Excel and have Excel graph the regression line here, and it would be something that looks about like this. And then if you then proceeded to use the equation of this line to do prediction, it should work very well. This line very well describes the trend of the data. So if this were weights and mileages of cars, then to know the weight of the car would almost perfectly predict the gas mileage of the car. On the other hand, you could be in a situation where the correlation is 0 or very, very small. If you went to Excel this time and asked Excel to generate a regression equation, it would do so, and I don't know what it would look like, basically some random line practically. You would get a regression line, and you could proceed to plug X values in and crank out Y values. So for example, plug in weights and get gas mileages. But those wouldn't mean anything because this line in this situation doesn't capture the trend of the data at all. In fact, there is no trend of the data to be captured. And so the moral of the story is, if you have a regression line in hand, you first better check the correlation. If there is strong correlation, either positive or negative, it's probably okay to go ahead and use the regression line to do prediction like we just did. But if the correlation is close to 0, then you probably don't want to use the regression equation. It doesn't mean anything. Here's another caution. How about we take our regression equation and we find the gas mileage of a 10,000 pound truck, a garbage truck or something. So okay, y equals 44.2 minus 0.00708 times x, which in this case is 10,000, and we get negative 26.6 miles per gallon, which is really an amazing car that gets negative 26 miles to the gallon. I don't know if that means that every so often you have to stop and drain gas out of the tank, or whether it means the longer you drive, the farther away you get from where you really want to go. Or anyway, it's a nonsense number, and we need to be aware of the possibility that this type of thing might happen. So why does it happen? Well, let's take a look at the data. Here's weight and mileage. And we had data that looked roughly like this. It was falling in the 2,000 to 5,000 pound range. And then when we asked Excel to do linear regression, it drew a line that looks something like this. And now we come along with a car or a truck that weighs 10,000 pounds. So when we plug a x value into a function like this, graphically it's the same thing as taking that x value, going up or down until you hit the line, and then going over and reading off the y value. So if I picked a 3,000 pound car and asked for its mileage, I'd come to 3,000, go up and over, and the mileage of the 3,000 pound car, predicted mileage, would be around in here. If I do that with my 10,000 pound truck, I go down to hit the line and then over, and my predicted mileage is here, and this is the negative 26.6. So the mathematics is working beautifully, and yet the answer is complete nonsense from a practical point of view. So what's went wrong? Well, we've used this regression equation. We've plugged in a value into the regression equation that's way outside of the norm for our typical data. This whole model, all of my other data was in the 2,000 to 5,000 pound range, and the model, the regression equation, probably works pretty decently in that range. When I get outside that range, that's called doing an extrapolation, and it's a very dangerous game. The reliability drops off. If you think about it, what would the mileage be for heavier vehicles? I mean, they can't physically go negative, so if you had more vehicles available, you'd probably see something like this, that the mileages would taper off and get smaller and smaller and smaller and never actually go negative. And so the line is really not the right shape to fit this data. If I had all of the data available, I probably want to choose some sort of curve that went like this and do a different kind of regression. We won't do that in this class, but the point is that you shouldn't attempt to use the regression equation outside of the range for which it was designed to be used. And likewise, you shouldn't use the data for practical situations that are different. So even if we were able to find a tractor, for example, that weighed 4,000 pounds, I shouldn't attempt to use this regression equation because the equation was derived using cars, not tractors. Okay, let's finish with a topic called multiple regression. This topic is not discussed in the textbook, I don't believe, and it is something that you are responsible for, and it will be the background for your fourth and final course project. Let me read this. In some situations, the regression equation giving the automobile gas mileage as a function of weight may not predict mileages with sufficient accuracy. Our R was negative 0.87, but that's not negative 1 or positive 1, which would give perfect accuracy. So, in particular, there are cars of the same weight that get different gas mileages. And why is that? What are some other features of a car that also influence its gas mileage in addition to weight? And let's stay with features of the car itself. I mean, the driving habits of the driver, of course, influence the gas mileage, but that's not a characteristic of the car, that's a characteristic of the driver. Likewise, the road conditions influence gas mileage, but that's not a characteristic of the car either. So some other characteristics of the car itself would be things like engine size. Some cars have bigger engines than others even though they weigh the same, and that makes a difference in the mileage. Wind resistance. So there's a very definite reason that cars have the shape they do. The engineers who designed them are trying to cut down on the wind resistance and therefore lower the wind resistance and raise gas mileage. Things like tire size also has a bearing on gas mileage, and there are probably others that you could think of. I'm going to focus on weight, which we've already been doing, weight of the car, and engine size. So now here's the data table that we had before, but extended. Here's the weight, here's the mileage of all of these cars, and now here is the size of the engine in liters. And so you see that some cars, like a Cadillac, has a large engine, probably because it's a heavy car and you need a lot of power to move that. But other cars, like a see if I can get my eye on it. A Corvette has a very large engine, even though it's not necessarily a particularly heavy car, and that's characteristic of sports cars where the engineers are seeking high performance. So the thought comes to mind now, I know the weight of a car and I know its engine size. Can I predict its mileage? Well, sure, if I can predict the mileage using weight. If I have both of these, surely I can predict its mileage. And maybe I can do a better job of predicting its mileage if I have more information about the car to use. Okay, let's go back to our Excel spreadsheet. And here are the weights, mileages, and engine size out of the table. I think I'll first go ahead and clear out some information here that we had before. Okay, and let's discuss how we might use both weight and mileage to predict engine size. I'm going to have Excel do regression again. So over to the data analysis, pick regression. For the Y range, oh, I see that I'm going to have to do something else. Let me do something else first. I am going to copy the weights. Let's see. I want to have the weight and the engine size side by side. So I think I will copy this information. So left click, drag down, right click, copy. Then I'll come over to cell D1 and right click and paste. Okay, I need the weights and the engine sizes right side by side. And to match what I'm going to be demonstrating, I actually want the engine size to the right of weight. So I'll copy it over here. If you think ahead, you don't have to do all of this information, all of this maneuvering around. Actually, now let me go ahead and delete this and this. Okay, so here is how I want things to be. Mileage and then weight and engine size in adjacent columns with weight on the left. Now let's go ahead and do data analysis regression. For input the Y range, the output is still going to be mileage. Input the X range. There are several X variables now. Weight is a independent variable, an input variable, and so is engine size. So I'll click and drag not only down but right and highlight this 2-column block here. Alright. And for output range, it's proposing to put the output in and around cell E1. That's fine with me, and everything else in this table can stay as given. So now I click OK and get an output. Here is an R squared again. It's now 0.788. That's a little higher than what we had before. The R squared before was like 0.75 or so. So we've raised the R squared a little bit, and that's a good thing. The higher the R squared, typically, the better predictor the regression model is going to do. And now here are some numbers that I'm interested in. 41.47, negative 0.00535, and negative 0.950. It's very important to keep track of the order. So the X variable for this line came from the weight column, and the X variable for the bottom line, came from the engine size column. Okay, so let's come back, and here is the output copied. And now here's an example of how you might use this. Predict suppose a 3,000 pound car has a 3.5 liter engine. Predict its mileage as accurately as possible. As I commented, the R squared is higher using both weight and mileage, using both weight and engine size than it was just using weight. So I will indeed use the engine size information as well. And now here is the form of the regression equation. I'm looking right here, and let me write this in standard mathematical notation. 41.47 roughly. then minus 0.0053 x, and I'm going to call it x sub 1 because there are a couple of x variables, and then minus 0.95 x2. What's what in this equation? This is mileage. This is weight. And this is engine size. And so for our specific numbers, y equals 41.47 minus 0.0053 times 3,000 minus 0.95 times 3.5. And if you work that out, 22.1 miles per gallon. Okay, multiple regression refers to the fact that there are multiple x variables, or multiple predictors, they're called. And the goal of using multiple predictors is to be able to get more accurate results than if you just had a single predictor. Thank you.